In this video, we're going to look at some examples for the integral test and a couple warnings. To start out with reminding ourselves of the integral test, as long as we are looking at the series for a sequence that is generated by evaluating a continuous, positive, and decreasing function at the integers, then if we just evaluate the improper integral of that function from 1 to infinity, we will be able to determine the convergence of that improper integral. That will then correspond precisely to the convergence of the associated series. So the first example we'll consider is the series 1 over n squared plus 1 and the associated function 1 divided by the quantity x squared plus 1. Now, if you look at this series and you're considering convergence versus divergence, recall that we know that the p series, sum of 1 over n squared from 1 to infinity, that was convergent. When you add 1 to that denominator there, how much difference could that really make? So you might have a conjecture in the back of your head that this series does converge. And so it can be helpful to have that in the back of your head as you go through this process. So the function that we're considering, 1 over x squared plus 1, is the associated function. We are satisfying the integral test because that function is continuous, defined for all values of x. It is positive because you've got a squared plus 1 in the denominator, and it's decreasing. And the reason it's decreasing, I always want you to justify this in some form when you write this down. One can either use a derivative argument, or in this case, I think the easiest choice is just to note that it's 1 divided by a quantity that is increasing. So if the denominator continues to get bigger, then the overall value would therefore be decreasing. So we're going to evaluate the improper integral of this function, and that means take the limit as t approaches infinity of the integral from 1 to t of 1 over x squared dx. 1 over x squared is the derivative of the inverse tangent function, arctan. Therefore, when we evaluate this integral, we're really evaluating arctangent from 1 and at t, and we're going to take the limit of that. And so that means we're taking the limit of the inverse tangent of t, and then here I got pi over 4. That's because I'm looking for the angle theta, where when you take its tangent, you get out 1. And the angle where the tangent is one where the sine and cosine values are the same, and that happens at pi over 4. So then we're going to take the limit as t approaches infinity. This pi over 2 here is obtained because the inverse tangent function looks like this. It's got 2 lovely horizontal asymptotes at pi over 2 and at negative pi over 2. We see as the value of t grows to infinity, we're spitting out outputs of the inverse tangent function close to pi over 2. As the slope of the tangent gets greater and greater, as the value of the tangent gets greater and greater, this is corresponding to angles closer and closer to pi over 2. So pi over 2 minus pi over 4 is pi over 4. This is finite. Since we determined that the value of the improper integral is finite, that means the improper integral is convergent. And by the integral test, the associated series, the sum from 1 to infinity of 1 divided by the quantity n squared plus 1 must also be convergent. So that's a classic example of how you apply this. In this next example, things are slightly trickier. We're going to look at the series natural logarithm of n over n and determine whether it converges or diverges. So the first thing we need to do, again, is check for continuity. The function is a quotient of continuous functions on the interval from 1 to infinity, so we're okay there. The second thing we have to check is positive. Here we have to be careful. The value of the natural logarithm of 1 over 1 is actually 0 over 1 or 0. So this is not positive at 1. It is, however, positive once we get to 2. So it's positive on the interval from 2 to infinity, or really numbers bigger than 1, but we need to correlate evenly with the series that we're looking at, so we would start at 2. And notice that's fine. Because of the fact that the first term of this infinite series happens to be 0, you might as well start your whole series at 2 anyway. So we might as well instead consider finding the convergence of the improper integral n equals 2 to infinity natural logarithm of n over n. But now we have the third consideration. We have to talk about whether or not this function is decreasing on the interval from 2 to infinity. Well, if you compute the derivative of the associated function, so our function is log of x over x. If we compute the derivative of that function, we get 1 over x times x minus 1 times natural logarithm of x all over x squared. So we have 1 minus the natural logarithm of x over x squared. Now if it were decreasing, we would want the derivative to be less than 0. And what we obtain is that f prime of x will be less than 0 when the logarithm of x is greater than 1. This implies x has to be bigger than the number e. Well, that's going to tell us we don't want to start looking at this series at 2 because 2 is smaller than e. We actually want to start at 3 because e is greater than, or e is a little less than 3. So this implies that what we're really going to have to do is the integral test will only apply if we go and look at the series starting at 3 of the natural logarithm of n over n. And then we can associate that to the improper integral of the natural logarithm of x over x dx. And the stipulations needed for the integral test will be satisfied. So, of course, we have the problem that that's not the original series we were considering, but notice that we just have to add log 2 over 2 to the series that starts at 3. If it turned out that this series starting at 3 converges, then adding another finite number to it will still give us a finite sum. If it turned out that this series from 3 to infinity of log n over n diverges, once we evaluate this improper integral, then we would know additionally it'll still diverge when I add a finite number. A sum that's already infinite will be infinite when you add more to it. Okay, so that's what we're going to do, is the integral test for improper integral log x over x evaluated starting at 3. So we have the improper integral of 3 to infinity, the natural logarithm of x over x dx, which is going to equal the limit. I'm going to use r's, not t's. R goes to infinity, 3 to r, log x over x dx. Then I'm going to notice this is a good candidate for a u substitution. If I let u be the natural logarithm of x, then du is 1 over x dx. Therefore, I can change variables, and I have the limit as r approaches infinity of the integral from the natural logarithm of 3 to the natural logarithm of r of u du. So we have the limit r goes to infinity of 1/2 u squared, evaluated at natural log 3 and natural log r. So we're taking the limit as r approaches infinity of 1/2 natural log r squared minus 1/2 natural log of 3 squared. Well, even subtracting off this finite number here, the natural logarithm of r as r approaches infinity will become infinite, so will its square. This is going to infinity, therefore this is a divergent value. Since the improper integral from 3 to infinity, the natural logarithm of x over x diverges, this implies, by the integral test, the series from 3 to infinity of natural logarithm of n over n diverges, which implies, since we're only adding terms, that the more extensive series from 1 to infinity of log n over n is also divergent. So this was a perfect example to remind us of a couple key features, warnings. In order to use the integral test and make a proper conclusion, we actually need to satisfy all the requirements. So you have to have this positive, decreasing, and continuous condition. In some sense, the way we use left and right-hand sums to bound divergent improper integrals and convergent ones, respectively, won't work if we don't have all of these happening. The continuity is required in order for us to compute the value of the integral, and the positive and decreasing in order for the proper relationship to exist between the series and the integral. If the function is positive, continuous, and decreasing for all x greater than or equal to another number a, we can, for instance, in my example in the previous slide where we were bigger than or equal to 3, then I can play the following game. Rewrite the series instead as the sum of these prior terms and then the part where the integral test will apply. This is the way we tend to think of it. Just list out that finite number of terms before. Might be 1, might be 2, could be 100, although you'd have some work to do. And then you just determine the convergence of the series starting at a by corresponding it to the improper integral from a to infinity of the associated function. So you just go past any problems such as discontinuities or issues of it changing direction, provided there's a point after which the function will stay positive and decreasing. If the function is negative and increasing everywhere, you could determine the convergence of the associated series. I don't know why that's a negative one. That should be a positive one there. So you could find the convergence of the improper integral associated to -1 times f of x. So since that would therefore be a positive and decreasing function. And then the properties of the convergent series allow us, if we find that the series of -1 times f of n converges, then the series +1 times f of n would also converge. So that's a trick. But if you have a function that doesn't have exclusive directional behavior after an anchor point, so it changes direction or sign infinitely often or has infinitely many discontinuities, you can't apply the integral test. And the key examples of this are going to be things that have oscillating trigonometric functions in them. So things like the series n equals 1 to infinity of cosine 3n over n plus 4. This is a horrible candidate to use to determine via the integral test because of the fact that the numerator cannot be written as an exclusively positive and decreasing function. You're going to have trouble. So those are the key warnings and information about using the integral test. I'll leave one additional solution in the slides for this video, but I think talking through it will make it too long, so we'll stop there.